For me, they're some of the most elegant creations in the world. But let's be real, they can also be seriously challenging. Today, we're checking out another cool paper from DeepSeek. It dropped last August and just got accepted to ICLR 2025. Congrats to the team. Their model, DeepSeek-Prover-V1.5, tackles tough proof problems using Lean 4. Now, if you're not familiar, Lean 4 is this awesome system that lets you build proofs step by step, with every move rigorously checked. For example, here's how you'd prove Euclid's theorem that there are infinitely many prime numbers. Sound fun? Let's dive in and see how the model handles it.
Let's dive into this paper, which introduces DeepSeek-Prover-V1.5, an advanced AI model designed for theorem proving in Lean 4, a formal proof system. If you're familiar with its predecessor, DeepSeek-Prover-V1, you'll notice this version is all about improving training and inference efficiency. The model starts by training on DeepSeek MathBase, a dataset specialized in formal mathematical languages. Then, it undergoes supervised fine-tuning, using an improved dataset. Finally, it's enhanced through reinforcement learning from proof assistant feedback. A fancy way of saying it, learns by getting feedback from Lean 4 as it tries to prove theorems. One of the big technical innovations here is RMaxTS, a variant of Monte Carlo tree search. Instead of just searching for proofs in a straightforward way, RMaxTS explores proof paths using intrinsic rewards. This means the model is encouraged to try new, diverse strategies rather than repeating the same ones. And the results? Pretty impressive. On the MiniFi 2F benchmark, which focuses on high school level problems, DeepSeek-Prover-V1.5 hits a 63.5% pass rate. For ProofNet, an undergraduate level benchmark, it achieves 25.3%. That's a solid improvement over its predecessor and other baselines. Let's take a look at Figure 1. It shows these results visually. The bar chart clearly highlights how DeepSeek-Prover-V1.5, which is fine-tuned, outperforms its pre-trained version and other models like Intern, LM two-step prover, Hypertree proof search, and Lemma. The improvement is especially noticeable on MiniFi 2F. So what's the big takeaway from this section? DeepSeek-Prover-V1.5 brings three key contributions: a more efficient theorem-proving model, an advanced tree search strategy, RMaxTS, and state-of-the-art performance on formal proof benchmarks. Now let's talk about why theorem proving is such a tough nut to crack. Language models like GPT-4 have made huge strides in natural language processing, but formal systems like Lian and Isabelle demand extreme precision. It's not just about understanding math, it's about structuring it in a way that these proof assistants can verify. There are two common strategies for theorem proving with AI. The first is proof step generation, where the model generates each proof step individually and checks it before moving forward. This is precise but slow. The second is whole proof generation, where the model writes the full proof at once and lets the theorem prover verify it afterward. This is faster but riskier. If the model makes a mistake early, the entire proof can go off track. DeepSeek-Prover-V1 used the whole proof method and achieved state-of-the-art results in Lean 4. But it had a problem. The model couldn't correct itself mid-proof, leading to cascading errors. DeepSeek-Prover-V1.5 introduces a solution, a truncate and resume mechanism. Here's how it works. Start with whole proof generation, let Lean verify it, and if an error appears, stop and fix it before continuing. Instead of regenerating everything from scratch, the model keeps what worked and only replaces the incorrect part. To make this even better, they integrate this into Monte Carlo tree search, MCTS, where the search policy decides where to truncate and retry. They also introduce curiosity-driven exploration, allowing the model to explore proof strategies beyond just following rewards. The result? A more flexible theorem, proving AI that balances speed and accuracy while learning from its mistakes. Now let's dive into how DeepSeek-Prover-V1.5 is trained and tested. There are three phases of training. Pre-training. The model learns from a massive dataset of mathematical and formal proof data. This is where it gains general familiarity with formal languages. Supervised fine-tuning. It's given incomplete theorem proofs and learns to predict missing tactic states and complete proof steps. Reinforcement learning. The model generates multiple proof candidates, and Lean checks which ones are valid. The valid proofs provide a reward signal, refining the model's parameters. Quote, for inference, The model works in two ways. It can do single-pass sampling, where it just generates a full proof in one shot, or it can use Monte Carlo tree search, MCTS, exploring various proof paths to find the best option. If you look at Figure 2, it visually breaks down this process. You'll see prompts and responses in Lean's proof environment, along with a code snippet for how proofs are structured. Some proof steps pass, others fail, and each attempt feeds back into the learning loop. The contribution summary highlights how the model benefits from its strong pre-training on a high-quality math dataset, the fine-tuning process that teaches it theorem completion, and the tree search algorithm that aids in long-term proof planning. Having this interactive feedback loop during MCTS is key to tackling more complicated proofs. Here, we continue with more training details, especially reinforcement learning and tree search. In the reinforcement learning stage, the model is fine-tuned with actual feedback from Lean. A proof that passes Lean's checks is rewarded. If it fails, that feedback helps adjust future predictions. We're calling this reinforcement learning from proof assistant feedback, or RLPAF. Next up is the introduction of MCTS with a special twist called RMaxTS. This approach doesn't simply search for immediate proof success. It also encourages exploring diverse strategies. This is crucial because proofs often have sparse rewards, and a curiosity-driven exploration can help the model escape local optima. Now let's talk results. The model was tested on two benchmarks, MiniFi 2F and ProofNet. On MiniFi 2F, DeepSeek-Prover-V1.5 achieves a 60.2% pass rate, up by 10.2 percentage points over the previous version. Adding tree search boosts that to 63.5%. On ProofNet, it started around 21.6% on validation and 23.7% on test sets, then climbed to 25.4% and 25.3% with tree search, a new state-of-the-art. The section then begins describing how the model is trained. It starts with pre-training on large-scale formal language datasets like Lean, Isabelle, and MetaMath. That gives it a robust foundation. Afterward, the model goes through supervised fine-tuning, where additional data, including explanatory comments, are introduced, aligning the AI's natural language reasoning with formal proof steps. Here, we get into the finer details of data curation, natural language reasoning, and tactic-aware augmentations. First, data curation. The model works with a Lean 4-proof dataset drawn from various sources, MATLAB4, older DeepSeek-Prover-V1 data, and validation sets like MiniFi 2F and ProofNet. In an expert iteration loop, the model repeatedly generates proofs, verifies them, and is retrained using the corrected outputs. Over time, explanatory comments get added, leading to a dataset of nearly 9.6 million sequences. Next, there's thought-augmented proof generation. Human mathematicians often explain their reasoning. Similarly, this model uses natural language reasoning before generating its final formal proof steps. It's similar to chain of thought. First, the model sketches out the reasoning in plain language, then translates that into step-by-step Lean tactics. This structure makes the proof generation more transparent. Finally, the paper discusses prompt augmentation with tactic state information. The model extracts each proof step's before and after states from the Lean REPL. Then it appends these states as comments in the code. During fine-tuning, these detailed prompts help the model spot and correct errors more efficiently. All of these enhancements, better data, chain of thought reasoning, tactic states, make the model more robust at theorem proving. Now let's see how reinforcement learning is specifically applied. The main goal here is to train the model using proof verification feedback from Lean 4 itself. First, there's the selection of prompts. The model is given a subset of theorems from the supervised fine-tuning dataset. Challenging ones it can solve sometimes but not always. After filtering, about 4,500 unique theorems remain, each paired with prompts that work in both chain of thought mode and standard mode. Next, let's talk rewards. Instead of a typical reward model, the system relies on Lean 4's verification result. If the proof is valid, it's a 1. If not, it's 0. This can be tough because it's a very sparse reward. Many attempts might fail outright. To keep the learning signal useful, the training process focuses on theorems that are not too easy, but still solvable. Rather than using proximal policy optimization, PPO, they opt for group relative policy optimization, GRPO. GRPO doesn't require a separate critic and compares multiple generated proof candidates in batches, adjusting the model based on their relative performance. That means the model picks up on which proofs are relatively better, even if most are incorrect. For the training specifics, they use the supervised fine-tuned model as both the initializer and reference. They set the learning rate to 5E6 and use a batch size of 512. For each theorem, 32 candidates are generated, and a KL divergence penalty keeps the model from drifting too far from its original, supervised, fine-tuned state. By directly learning from real lean verification rather than a static dataset, the model gains adaptability and accuracy for tackling trickier proofs. So how do we evaluate the model and all these training setups? We look at two benchmarks. First, MiniFi 2F, which targets high school level algebra and number theory problems from competitions like the AMC, AIME, and IMO. There are 244 validation and 244 test problems, originally in Lean 3 but converted to Lean 4. Second, ProofNet, focusing on undergraduate level math, including real analysis, linear algebra, and topology. It has 185 validation and 186 test problems, also converted to Lean 4. The model is tested with different prompting styles. For MiniFi 2F, they use human-written examples in a few-shot setup, and for ProofNet, they use previously generated correct proofs. They compare two approaches: chain of thought, or COT, prompting, which breaks things down step by step, and non-COT prompting, which is more direct. Check out Figure 3 and the accompanying table if you can. You'll see how performance changes from pure supervised fine-tuning, which gets close to 50% on MiniFi 2F and 15.9% on ProofNet, to reinforcement learning, which bumps them up to 51.6% and 18.2%, respectively. COT consistently outperforms non-COT, reinforcing that structured reasoning helps. They also discuss pass at K, which is the chance that at least one proof is correct within K attempts. The model runs on an A100 GPU, uses temperature/top-P sampling, and has a 2048 token limit per proof. Lean 4 has a 300-second time cap for each proof verification. These details matter if you're trying to reproduce or compare results. Next, let's compare the different training stages for DeepSeek-Prover-V1.5. The base model, DeepSeek-Prover-V1.5 base, already solves about a third of MiniFi 2F's with 3-shot prompting. Supervised fine-tuning, however, really boosts its accuracy, about a 66% increase on MiniFi 2F's and a doubling on ProofNet. Throw in reinforcement learning, and you get another jump in pass at K accuracy, meaning it's more likely to get a correct proof within multiple tries. This improvement, unlike in natural language math tasks, isn't just about ranking the correct proof higher. It genuinely helps the model find correct proofs more reliably. The comparison between COT and non-COT shows COT is consistently better, because it forces the model to plan the proof steps in a structured way. With reinforcement learning, DeepSeek-Prover-V1.5-RL ends up at 51.6% on MiniFi 2F and 18.2% on ProofNet, demonstrating the value of structured reasoning. Then we move to Monte Carlo tree search, MCTS. The key idea is tactic-level tree abstraction to the step. Instead of one large generation, the proof is broken down into nodes representing each proof step. If part of the proof fails, the model can resume from a valid checkpoint rather than regenerating the entire proof. They use a truncate and resume mechanism to sample. The model initially produces a complete proof, but if Lian finds an error, the proof is truncated right before the error. That valid prefix is saved as a node, and the failing part is fixed. It's basically step-by-step debugging that uses a tree structure. This approach greatly reduces wasted computation and makes the model more efficient. Now let's see exactly how MCTS corrects errors efficiently. The proof starts off incomplete, with a theorem statement and some initial steps, plus a comment describing the tactic state. The language model proposes the next proof step, then everything is checked in Lean 4. If the proof passes, we're done. But if there's an error, we cut off at the mistake and save everything before it as a verified prefix. Those verified steps become a node in the search tree. From there, the model continues, branching out into different ways to fix or complete the proof. That's how multiple proof paths form a tree structure, each path representing a unique strategy. The resume mechanism ensures we're not just endlessly repeating the same code. If multiple tactics lead to the same underlying logical state, the system can store them and revisit them later. It randomly selects one to prompt the model, ensuring more exploration variety. By doing this, the model not only recovers from mistakes, but also picks up knowledge from successful partial proofs, making the entire search process more robust. Here we explore how MCTS is structured into selection, expansion, simulation, and backpropagation. We'll concentrate on selection and expansion. In selection, we start from the root node, the empty or partially completed proof, and navigate down through the tree to find the most promising path. It's a balance between exploiting what's been successful and exploring untried avenues. Each node has a score based on success rates and an exploration bonus, so the system doesn't only follow well-known paths, it also tries out less explored options. Once a node is chosen, we move to expansion. That's where the language model resumes from that node's partial proof, generating the next sequence of steps. Lean checks the new steps. If it verifies them, great. If not, the proof is truncated at the first error, and only correct steps are added to the tree as child nodes. Unlike some classic game tree searches that only add a single layer per expansion, theorem proving can add multiple steps at once, since it's a sequential reasoning task. This allows for a more efficient approach to building or correcting larger chunks of the proof. Sparse rewards are a big challenge in tasks like theorem proving. Typically, you only find out if you succeeded or failed once the entire proof is complete. That's not very helpful for guiding intermediate steps. Here's where intrinsic rewards come in. Instead of just waiting for the end, the model also gets a small reward each time it expands the search tree with a new node. This encourages broader exploration. It reduces situations where the model generates the same incomplete proofs over and over, because you get some credit for discovering new states, even if they're not yet a full solution. They also use a technique called UCB for non-stationary rewards. This helps the model decide which action or path to pick, balancing known successes with underexplored possibilities. If a path has high success, or hasn't been tried much, it gets a higher priority in selection. This way, the system avoids getting stuck on a single approach, and continues to discover new ones. All of these tweaks help MCTS handle the complexities of formal theorem proving. Another technique mentioned here is discounted upper confidence bound, DUCB. The idea is that older proofs may become less relevant over time, so DUCB gradually discounts their influence. This encourages the system to keep exploring fresh tactics, instead of clinging to past successes that might not generalize. They also scale up the search with parallelization. First, root parallelization runs multiple instances on each GPU, so verifications can happen simultaneously. Second, tree parallelization spreads different proof search tasks across worker threads, balancing generation and verification. And then there's virtual loss, which temporarily assigns a zero reward to a proof path so the system doesn't get too fixated on it before it's fully explored. Together, these approaches boost speed and ensure that no single strategy takes over prematurely. The result is a faster, more diverse search process, which is essential for tackling large-scale theorem collections efficiently. Often in formal theorem proving, there are two main styles. One is multi-pass proof step generation, where you verify every small step as you go. The other is single-pass whole proof generation, where you generate the full proof and then verify it all at once. DeepSeek-Prover-V1.5 blends the two. It generates a whole proof in a single pass, but if something's wrong, it truncates and resumes from the last correct step. That way, it's not starting from scratch after each error. This approach combines the caution of stepwise methods with the speed of whole proof generation. In terms of benchmarks, the paper evaluates Minify 2F, high school level problems, and ProofNet, undergrad level problems. The authors also compare DeepSeek-Prover-V1.5 with other AI models, including GPT-4, and specialized theorem proving systems like Lemma. The hope is that by weaving together ideas from formal theorem proving and large-scale language models, they can push automated proof generation even further. This part contrasts well-known approaches to theorem proving with language models. Tools like GPT-F use step-by-step generation, verifying each step as they go. Others, such as DSP and Lego Prover, produce the entire proof in one shot, then verify it. DeepSeek-Prover-V1.5 takes a middle ground. It does a single-pass generation, but it has that helpful truncate and resume process if errors pop up. Performance is measured with pass at k, basically, whether a correct proof shows up in any of k attempts. Different sampling strategies define how these attempts are counted. The results. On Minify 2F, the new RL version of DeepSeek-Prover-V1.5 hits 60.2% success in whole proof mode, a strong jump from older versions. With tree search, it rises further to 62.7%. On ProofNet, it scores 22.6% and 25.3%, beating out models like Reprover and Intern LM two-step prover. This underscores that combining reinforcement learning with a structured approach to searching proofs yields significant benefits. Here we compare single-pass generation to tree search on the Minify 2F dataset specifically. Check out the relevant table if you can see it. Single pass, DeepSeek-Prover-V1.5-RL notches 60.2% accuracy. That's already quite high, but as we increase the sample budget, meaning we allow more attempts, the gains start to plateau a bit. Tree search. When DeepSeek-Prover-V1.5-RL is paired with RMaxTS, we see 63.5% accuracy, which is currently the best reported performance. Other tree search approaches like intern LM two-step prover and LeanStar do well too, but they can't match DeepSeek-Prover-V1.5-RL with RMaxTS. So this really highlights how reinforcement learning and tree search methods synergize. The synergy yields even better theorem-proving performance than either approach on its own. Now let's talk about the ProofNet dataset, which is more advanced. The table here shows both single-pass and tree search results. On single-pass, DeepSeek-Prover-V1.5-RL outperforms its earlier versions with about 22.0% test accuracy. That's a marked improvement over the supervised fine-tuned version, but tree search continues to add value. DeepSeek-Prover-V1.5-RL plus RMaxTS reaches 25.3%, the highest we've seen. They also mention that large-scale sampling strategies contribute. Reinforcement learning with compiler feedback helps the model produce valid proofs more reliably, and chain-of-thought prompting appears to add extra diversity to the model's proof planning, further enhancing accuracy. It's another instance of the central theme. Combining RL, tree search, and structured prompts leads to better results than trying any one of them in isolation. We return to the topic of chain of thought, COT, versus non-CoT approaches. CoT means the model explicitly walks through proof reasoning in a detailed manner, while non-CoT relies on lean automation to fill in the details without that explicit breakdown. From the table shown here, CoT outperforms non-CoT. But the real winner is actually a hybrid approach that taps into both. By splitting the proof attempts, some with CoT, some without, the accuracy peaks at around 63.5%, which is the best result noted in this study. So why does mixing them work? CoT is great when the problem demands detailed logical reasoning, and non-CoT can be more efficient when Lean's automation can handle the complexities. Pairing the two strategies broadens the model's skill set. They also talk more about RMaxTS, the specialized tree search approach. It uses intrinsic rewards to encourage exploration and discounted UCB to balance old and new successes. This keeps the search process nimble and open to new proof strategies. Overall, these experiments show that structured reasoning plus automation plus a solid search algorithm is a powerful combo for theorem proving. Here, the focus is on how RMaxTS is tested in different configurations. They investigate whether including tactic state information in the prompts helps. The verdict? Absolutely. When the model expands proof steps without that context, the performance dips. But with tactic state info, it does much better, indicating the importance of having a clear picture of the intermediate proof state. Different RMaxTS variants are also compared. Standard RMaxTS, with all the bells and whistles, intrinsic rewards, tactic state guidance, etc., yields the highest accuracy, around 62.7% with a larger sample budget. If they remove certain components, like intrinsic rewards or tactic state feedback, accuracy drops, which reinforces how crucial those ingredients are. This part drives home the fact that fine-tuned details matter a lot when designing a search algorithm for theorem proving. Combining reinforcement learning with robust tree search leads to major performance gains. Finally, we take a look ahead at potential future directions. One main challenge remains: balancing exploration and exploitation. While RMaxTS does a solid job at promoting proof diversity, the authors point out that the core problem of proof search is still wide open. One idea is to train a critic model that scores incomplete proofs, helping prune unproductive paths early on. That could speed things up and improve success rates even further. Another direction is working with multi-theorem lean files. Instead of just single statements, we'd have entire collections of theorems, definitions, and lemmas that form a larger theory. Models can handle some file-level context already, but there's a long way to go before they can handle real-world, mathematical formalization tasks effectively. At the end, the references highlight related efforts in RL, MCTS, and theorem proving, as well as research on intrinsic reward systems and exploration strategies. These references can be a good starting point if you want to dig deeper into the technical background. So that's where we stand. DeepSeek-Prover-V1.5 has made significant strides with a blend of supervised fine-tuning, reinforcement learning, and MCTS-based search, and there's a clear roadmap for how these ideas might be extended to tackle even bigger challenges in automated theorem proving.